What separates a powerful scientific truth from a comforting story? Think about it for a moment. We live in a world that's just absolutely saturated with information. Claims about the healing power of crystals, predictions from astrology theories about the origins of the universe. So how do we actually draw the line? How can we distinguish a robust, evidence-based idea from one that just sounds good? This isn't just an academic question. It strikes at the heart of how we build our understanding of reality. It's the difference between building a rocket that reaches Mars and building one that just looks like it should. The stakes are our collective progress and our grasp on the universe. In our last conversation, we explored theory validity. Evidence supports a theory. But is more confirming evidence the whole story? Imagine you have a theory and only look for things that prove you're right. You'll find them everywhere. We naturally love to be right, but true science demands something more rigorous. It requires deeper, courageous thinking. It asks not just what can prove me right, but more importantly, what could prove me wrong? The quest for a clear dividing line has been long, so we stand at a crossroads. Here comes our guide, a philosopher of science named Karl Popper. He looked at the scientific landscape of his time in the early 20th century and saw a problem. He saw new theories like Einstein's theory of relativity, making breathtakingly specific and risky predictions. Einstein didn't just say gravity affects things. He predicted that starlight would bend around the sun by a precise amount, an amount that could be measured, an amount that, if wrong, would have shattered his theory. Popper saw this as the hallmark of a truly scientific attitude. It was a brave declaration to the universe. Here is my idea. Prove me wrong. Popper contrasted this with psychoanalysis and with Marxism. He noticed supporters could interpret any event as confirmation. If a person acted a certain way, it confirmed the theory. If they acted the opposite way, the theory could still explain it and call it confirmation. There was no conceivable observation that could prove the theory wrong. For Popper, this was a red flag. An idea that can explain everything isn't a powerful theory. It's an intellectual black hole from which no light of refutation can escape. So Popper proposed his solution. He called it falsifiability. It's simple but profound. For a statement or theory to be scientific, it must be falsifiable. This doesn't mean it's false. It means there must be some conceivable observation or some experiment or some piece of evidence that could, in principle, prove it wrong. The theory must take a risk. It has to stick its neck out. That vulnerability is what gives a scientific idea strength and integrity. It's the ultimate test of its connection to the observable world. This became Popper's line in the sand. On one side, science, testable hypotheses, risky predictions, openness to being corrected by nature. On the other side, pseudoscience, unfalsifiable claims, vague prophecies, self-sealing arguments that block critical examination. It's not about whether an idea is true now. It's about whether it could be proven false. This single principle gives us a powerful lens to evaluate claims about reality. It's a tool for clear thinking in a complex cosmos. Let's make this concrete. Imagine you're an ambitious young ornithologist in 17th century Europe. You've traveled far and wide across your continent, observing swans in pristine lakes and meandering rivers. You've seen them in England, in France, in Germany. Everywhere you go, every swan you see is a brilliant, majestic white. After observing thousands of these birds, you might feel pretty confident in proposing a scientific law. All swans are white. This seems like a perfectly reasonable conclusion based on an overwhelming amount of evidence. You've done your homework, you have data, it feels scientific. Now let's apply Popper's test. Is the statement all swans are white a scientific one? According to the principle of falsifiability, the answer is a resounding yes. Why? Because it's incredibly vulnerable. It makes a bold, universal claim that can be shattered by a single observation. It's not just a summary of what you've seen. It's a prediction about every swan you haven't seen yet everywhere for all time. It takes a huge risk. All it would take to falsify your entire theory is the discovery of one, just one, non-white swan. This isn't just a hypothetical. European explorers eventually sailed to Australia. And what did they find there? They found swans, but these swans were not white. They were black. In that single moment of observation, the law, all swans are white, was utterly falsified. It was proven wrong. And this for Popper is not a failure of science, it is science in action. The old theory was tested and failed, clearing the way for a new, more accurate understanding. Most swans are white. Swans can be either white or black. Progress was made. The black swan represents the power of a falsifying instance. Notice that no number of additional white swans can prove the theory all swans are white with absolute certainty. You could count 1,000,000, 1,000,000,000, 1,000,000,000,000 white swans, and there might still be a black one hiding somewhere. But it only takes one black swan to disprove it. This asymmetry is crucial. Science, in Popper's view, doesn't advance by proving theories true. It advances by proving theories false, chipping away at ignorance and replacing weaker ideas with stronger ones that survive tougher tests. Let's break down the fundamental logic here because it's as elegant as it is powerful. A scientific theory, at its core, is a prohibition. It forbids certain things from happening. Einstein's theory of relativity forbids an object with mass from reaching or exceeding light speed. The theory, all swans are white, forbids the existence of a black swan. This prohibitive nature is what makes a theory testable. By telling us what cannot happen, it gives us a clear target to aim for. We go out and look for that forbidden thing. If we look and don't find it, the theory survives. It has withstood the challenge. It's been corroborated. That doesn't mean it's proven absolutely true. It just means it's a tough theory. Passed the test this time. The more specific and risky the prohibition, the more impressive its survival. Predicting the precise bending of starlight is a riskier bet than saying stuff falls down. When the risky bet pays off, confidence grows immensely. The real magic is when we do find the forbidden thing, the black swan, the particle moving faster than light. That's falsification. Logically, it's modus tollens. If T then P, we observe not P, therefore not T. This deductive certainty is what makes falsification decisive. Science is a game of high stakes. Every good scientific theory is a gamble, a bet against the universe. I bet you will not find a rabbit fossil in Precambrian rock. I bet you will not find a perpetual motion machine. By making bold, falsifiable bets, science invites the judgment of reality. It's a humbling process. It forces scientists to be critical of others' ideas and their own. That critical spirit drives discovery, refining ideas, and getting closer to the truth. Now let's turn our gaze to the other side of Popper's line. What does an unfalsifiable claim look like? Astrology is a classic example. An astrologer might tell you, because you are a Scorpio, you will face a significant emotional challenge this week. This sounds specific, but is it? What counts as a significant emotional challenge? A disagreement with a friend, a stressful day at work, spilling your coffee. The prediction is so vague and open to interpretation that almost any event could be seen as confirming it. There is no clear, forbidden event. Let's say you have a fantastic week with no challenges at all. Does this falsify the astrological prediction? Not necessarily. The astrologer might reply with explanations that give the theory a built-in escape hatch for every possible outcome. It can't be pinned down. It can't be proven wrong, not because it's correct, but because it's not structured to be testable in the first place. It is insulated from reality. This distinction is not about ridiculing belief. It's about clarity. It's about understanding what kind of game we are playing. So has Popper solved everything? Is falsifiability the final word on what science is? Not quite. The universe is a complicated place, and so is the process of science. Big, complex theories like the theory of evolution, models of climate change, are not single statements. They are vast networks of ideas. Think of it this way. When astronomers in the 19th century observed that Uranus's orbit didn't quite match predictions of Newton's laws, they didn't throw out Newtonian gravity. Instead, they used Newton's theory to predict where a new planet should be, pointed their telescopes, and discovered Neptune. This shows that scientists often protect their core theories, and sometimes this is a very productive thing to do. Falsifiability is a powerful ideal, a guiding star for scientific integrity. It keeps science honest and tethered to reality. It reminds us that the goal is not to be dogmatically right, but to be progressively less wrong. It enshrines skepticism and critical thinking at the heart of the scientific endeavor. It's what separates the hard, uncertain work of discovery from the easy comfort of dogma. Without the constant threat of being proven wrong, science could stagnate into a collection of cherished beliefs, no different from the unfalsifiable systems it seeks to replace. Ultimately, falsifiability might not be the whole story of science, but it's a crucial chapter. It's a first principle for any aspiring explorer of the cosmos. In our next discussion, we'll dive into the work of Thomas Kuhn and his idea of paradigm shifts, where entire scientific worldviews don't just get falsified, they get overthrown in massive revolutions. For now, I leave you with a question. Think about a scientific claim you take for granted. What observation, what black swan, could possibly prove it wrong?